Uh, Thank you for the invitation. Also, thank you for the introduction. Okay. In this talk, I will introduce our recent um, understanding about the scaling law, in particular for the training of large language models. So this is the outline. So basically, we will first motivate why this is important to understanding the scaling law, and even beyond the scaling law itself. And then we will introduce the toy model for our analysis. Then the third part is about our result. The fourth part is about our so I will present some theoretical results deriving from our functional scaling laws. And the last part is about to validate our some the validation of our theoretical results. So it's currently well known that the large language model have become a driving force behind the modern AI, right? So basically, the training of a large language model can decompose into basically two stage, two parts. The first part, the most important part, is about the pre-training, and also is another important is about the post-training. But specifically in this talk, we will focus on the pre-training. So pre-training large language model typically involves solving the following optimization problem. Basically, we want to maximize the probability or the log likelihood of the next token prediction. Basically, you want to the probability of our model can predict the next token, the else token using all the tokens before XL. Here, the P theta typically is a very large scale transformer. For example, it has it at least have 10 billion parameters. And the distribution D is an internet scale data set. So basically, both the number of parameters and the number of data is huge for the pre-training of large language models. And the consequence is the pre-training is extremely computationally expensive. So our motivation is that if we can have some understanding about the pre-training, it may be helpful to reduce some computational cost. So let's first look at the training loss curve of the Llama 2. So basically, this figure is the training loss curve for the Llama 2 models of different sizes. So the red curve is the 7 billion parameters, the model's loss curve of the 7 billion parameters. And the blue one is for the model of 13 billion parameters. And then, so basically you have four size of models. So you can see that even the model has lots of parameters and it's trained on the the huge data. So loss curve is actually follows certain surprisingly simple patterns. For example, at least you can have a observation that is, for example, this is the x, the horizontal axis is about the process tokens, because in the pre-training we usually only go through data for one pass. So basically, you can interpret the number of tokens as the number of iterations for the optimization. So you can roughly see them as the equivalent metric, and the vertical axis about the training loss. So you can basically see that as you increasing the number of parameters from the red one from the 7 billion to the 70 billion, you can see that not only the loss, the final loss is reduced, but also the training becomes faster. So basically, the convergence rate is actually depends on the size of your models, and also for each model, the loss curve is actually quite simple. For example, you may think that we can use in certain, so basically our motivation is that if we can model this loss dynamics by, for example, because my background is from applied mathematics. So basically you can ask if that's, we can write one equation, so one-dimensional equations, differential equations, so that the equations can capture the pattern of the loss evolution during the training. So if this is possible, then we can use these equations to help us to design the better training strategies to achieve lower loss under the budget constraints. So the budget basically means the compute of the number of data. And actually this question is already been done in the community with the name called the scaling law. For example, basically the scaling law. So the first phenomena, which is a very consistent phenomenon, that is that the loss curve, the loss dynamics actually obey certain scaling laws. So basically, it tells us that if given a model size M and the data size capital D, so we have the loss actually follow the following power law relationship. So L0 is the irreducible loss, and this is the power law for the model size. It basically represents the approximation error, and this part is about it's scanning with the data set size, because as I mentioned that in the training in the pre-training, we usually only go through the data for one pass. So basically, the scaling about the data set size is actually about the scaling about the number of iterations. So basically, this part is actually represents the optimization error. It's not about the generalization error. It's actually the optimization error. So you can interpret the capital D as the number of iterations divided by the batch size. So, but this, so basically, this is a very important observations with this power law relationship. So you can so basically scaling have become a fundamental principle guiding the modern AI development because it actually tells us that when you increase in your number of parameters and the number of data, the performance of your model actually improve in the predictable manner. And moreover, it can be used in practice to design the training. So on the high level, it actually tells us a very fundamental principle, because the performance is improved in a predictable way. On the micro level, on the low level, it actually also can be helpful for design the specific training strategies. For example, because the scaling law that's only 5 parameters, right? The L0, capital A, little a, capital B, and a little b. So basically, you can done some experiments on very small scale, typically just one, like 100 million parameters, and then for example, if you have in the left figures, if you have this point and this point and this, if you have a 3 point on the small scale, you can use this small scale data to fit this scaling law. Then if you have this scaling law, you can then extrapolate to the larger scale. So basically that means before you train your model, before the training your model, you can predict the performance of your model in the larger scales. So this is the fundamental principle in the modern AI development. So for example, one of reality, it happens in practice that we can use this scaling law to design so-called compute optimal training strategies. So basically, if the budget, if we give a fixed compute budget thing, how should we allocate the model size, the data size to minimize the loss? Because when you have a fixed computer budget, there are 2 ways to improve the performance. One is to increase the model size, right? So if you increase the model size, you can reduce the approximation error. On the other hand, you can also increase the data size to reduce the optimization error. Then a natural question is, what's the best trade-off between the approximation error and the optimization error on the constraint of the compute budget. So in practice, you can do this. You can you can obtain the optimal trade-off by. So basically, you can first conduct some very small scale experiments. Then you fit the scaling law. Then you solve the following optimization, minimization problem. So basically, you want to, under the constraints, the 6 times the M and D is equal to C. So basically, the compute cost, because if your model have M parameters, if the model goes through D tokens, then the total compute cost is the number of parameters M times the number of tokens. So basically, if you already have the scaling law, which is obtained from the fitting small scale data experiments data, then you can use it to design the optimal trade-off by solve this optimization problem. But there's a problem, limitation about the scaling law. That is, okay, this is not well known for everyone, but I want to mention that actually the scaling law. So basically, this is the loss here. It's actually mean the final step loss. So basically, the scaling law, the vanilla scaling law predict. So given number of parameters, for example, 7 billion, and given the number of data, 2 billions, the prediction of the scaling is actually is about the final step loss. The final step loss. So the natural question is that, can we establish a certain similar scaling laws, dynamical scaling or functional scaling law, so that we can predict not only the final step loss, but also the whole training trajectory, at least for the loss, about the loss dynamics. So this is this is the first questions we want to ask. And also this question is actually relevant. It's not only for the research interest, actually very important for practice. For example, it's about it's important for us to understanding the learning rate schedule. So basically, in the large language pre-training, the most popular learning schedule is called cosine. So basically, the cosine schedule is given by the blue curve. So there's a half period of the cosine function from the max value decay to the minimum value of cosine functions. So this is the most popular, at least. I say at least 1 year ago, the most popular schedule in practice, and the most recently, a schedule called WSD, warm-up stable decay schedule becomes more and more popular, at least for the training of some large language model in China, in the China company, like the DeepSeek and the Kimi. So basically, they are using the WSD schedules. This schedule is very weird because it keeps a constant learning rate for a very long time, a long stable phase, and it only decays the learning rate near the convergence. So basically, only a very short duration for the decay learning rate, and most of the training of the steps is to keep a constant. So how can we understand the popularity of this very strange learning schedules? And more important, for the practitioners, that's a very strange observation when using the so-called WSD schedules. So this loss curve is from the Kimi K2. It's from the basically this loss curve is released from the Kimi company, the Kimi. So this is about 1,000 parameters model. So this is the loss curve. So you can see that during the stable phase, so basically this is a stable phase. During the stable phase, the loss decreases, but it gradually saturates over long durations. And then whenever you decay the learning rate, the loss, you will see a very fast drop of the loss occurs near the end of the training. So there's a question that is, during the stable phase, we can see that the loss decreases actually saturates. So then there's a question: should we decrease the learning rate as early as possible. As long as the loss decreases saturate, then we should decrease the learning rate, or we should keep a constant learning rate for a very, very long time. Don't care about the loss saturations. And then we expect that the loss can drop to a sufficient lower value during the decay phase. So what happens is either the first case or the second case. So how can we understand? So to answer these questions, we need to understand what happens during the two phase of the WSD schedules. So as I mentioned that it's actually, if we want to understand the loss dynamics, so basically all our questions actually about the optimization errors, the loss dynamics. So it's actually a traditional optimization, it's a traditional optimization problems. But it seems that to answer these questions, it's impossible to use the classical optimization theory. For example, one of the questions, in the optimization theories, the convergence rate is usually about the either n to the this one or this one or this one or the exponential one. But in the LLM pre-training, the convergence often exhibits this kind of power decay or normal decay, with the gamma can be a very strange value. Like in the Chinchilla law papers, the report value in their papers is 0.28. So what kind of properties of the data set or the model size determine these factors, this exponent? And another question is that in the traditional stochastic optimizations, so we typically, for the convergence analysis, we typically take the learning rate of a polynomial decay in this way. However, such schedules are never used in the training LLM, large language models, even the general deep learning models. And also, how can we understanding the two-phase loss dynamics under the WSD? So basically, this is our motivation. It's natural to so basically, you can ask the question: is the gap between the theory, the traditional optimization theory, and the practice is due to the non-convexity of the large language model pre-training? So it's very easy to give this kind of answers, because so what's the gap? The gap is because large language model is a very complex systems. It's a non-convex, so the huge parameters. So this it's not strange. So it's very easy to convince to others that it's not strange. You have these gaps. However, in this talk, I want to convince you that it's not. It's probably not. It's not the non-convexity or complexity of large language models cause this gap. It's actually our understanding, even in the very classical setting, we have never have a fully understand about the stochastic optimization. So basically, let's look at the very simple but very motivated experiments. So the left figure is a large language model pre-training loss dynamics. So the red curve is corresponding to the cosine schedules, but with the different total duration, total steps. And the blue curve corresponds to the WSD. It's have a different name in these papers, but it's WSD with different number of stable steps. So you can basically see this kind of figure, loss curves. On the right figure, actually, a linear regression, but it's a linear regression. But if you're using cosine schedule and the WSD schedules, so you can see the actual loss curve for the left one is the large language model pre-training. The right one is actually certain linear regressions, right? Certain linear regressions. So you can see they're actually very close to each other. For example, the WSD actually matches, even outperform cosine. And also during the for the WSD schedules, you also can see the very clean two-phase dynamics. You have a very long stable phase, loss decreases and saturates gap saturations and a sudden loss drop during the decay phase. And also, even in this linear regressions, if you compare in this linear regression, if you compare the performance of the cosine and the W schedule with the classical polynomial schedules, you will see that, for example, the green curve is and the orange curve is for the classical polynomial decay linear rate schedule. You can see that it actually performs much worse compared to cosine and the WSD schedules, the one used in practice. That means perhaps we can use this linear regression to understand what's the benefit of adopting the cosine and the WSD schedule compared to the classical polynomial one. So then what's the linear regression? Okay, so it's actually funny power law kernel regression problems. It's basically an infinite dimensional linear regression. So basically it's about the supervised learning. So let's X the input data and Y is our label. Epsilon is the F star is the target function. Epsilon is the noise. So assume the noise level is sigma squared. And the F star, the target function, is given by the combination of some feature functions. And the theta J star is the coefficients. But for simplicity, you can just think and the number of features as infinite. Okay. So without loss of generality, you can assume the feature function following certain Gaussian distributions. Okay. And with H denote the feature covariance, feature variance. And you can assume this diagonalized with the lambda 1, lambda 2, and the lambda n denoting the eigenvalue of the Hessian, of the H, the covariance. And to learn this target function F star, okay, we consider a student model with a finite weight M. So basically, so our model is still using the feature function, feature phi, but it actually uses a projection because the phi is a high dimensional feature. Our student model can only use the finite projection of our feature. Basically, typically there's two choices of the projection. One is the random projection. In this case, this is model corresponding to the classical random feature models. But in this talk, I will show you, and at least for the understanding, it's maybe easier to consider the toy model called the top M features. So basically, you can use the most important, the top M features. Because I want to mention that I forgot to mention that we assume the number 1 is bigger than number 2 and bigger than number 3. So the most important features, the top M features are phi 1, phi 2, and until phi m. So if we want to your model to the optimal choice of the features must be the top M features, and I will show you actually. So in this case, for a certain case, the random features is actually equivalent by using the random features is equivalent to using the optimal features. So this is our machine learning problem, learning a target function F star using a projection model. And our training algorithm. So let's look at the risk. So because the Y is a label, is a noisy label. So basically have the clean label plus the noise. And then we use the epsilon. This one denotes the excess risk. And this is corresponding to the label noise. So our algorithm is just a one pass SGD. So basically in each step, we're using the fresh data, sampling of fresh data. And the B is the batch size, and the eta k is the learning rate. You can rewrite the mid-batch gradient as the full batch gradient plus a noise. So noise has a mean 0, and the covariance 1 will be the sigma. So basically, the sigma vk is the covariance of our gradient noise corresponding to the base size 1. And then we call the eta, both eta as the linear schedule because the eta is not a constant in our analysis. Actually, we we are care about how the decay of the eta will influence the convergence of our training algorithm. So before we stating our statement, I want to give a perspective on understanding these learning problems. So basically, we can conceptually treat the normalized features because we assume that the phi j's are normalized. So basically, the phi j, the variance of phi j is lambda j. So you can normalize the phi j, the phi hat j as the we can call this as skews. Okay. So then our loss function is given by this one. So basically, that means that you can as the f star, the target function, as solving a task. So basically, you're solving one task maybe use many different skills, and the skills, the important are some skills are important, some skills are less important. So the number of the number j. So you can basically the target function represents superposition of infinitely many skills, and the number j will relative importance of each skills in these problems. And our model can, because if you consider top M features, our model can use only M skills. So basically solving this problem, essentially you need infinite many skills. But however, because your model has only finite parameters, you can, at the ideal case, you can, at most you can use the top M skills to solve this problem. Then you can expand this expression into three terms. The first term is the learner skills. So this term mirror the learnability of the top M skills, and this part is about the that's because you can only have the M skills. So there's the other skills. It's important to learn from the data, right? So actually, this one corresponds to the approximation error. And we also have the label noise. So this is the irreducible loss. And also we needed to define a certain concept called capacity and task to measure the model's capacity and the task difficulty. So basically, we can assume the number j, the eigenvalue, follow a power law, and the beta is the exponent. And we assume that the theta j star is the superposition coefficients also follow a certain power law. And the beta, so first I will say the beta is, we define the beta as a capacity index. It's because if you extract our student model using the normalized skills, normalized function, normalized features, you can see if the larger the model, okay, so the larger value of the beta, then your student model essentially use less number of features. For example, in the infinite case, if only the first and second eigenvalue is non-zero, the other eigenvalue are zero. So even it looks like you have an M parameter, but you can only essentially you are only using the top two features. So here the beta is a more smooth factor to characterize how. So it's like a capacity. So capacity is quantify how effective how many skills or how many features are used for your models. The S captures the relative difficulty of your task, because if you express your target functions using the normalized features, so the S quantifies the decay rate in the spectral space, in the feature space. So if the larger the S, the energy of your functions decay faster in the feature space. That means the problem becomes easier. So basically you can understand the S and the beta as quantify the task difficulty and the model capacities. Okay, and okay, so we still needed to introduce another very important concept called intrinsic time. So this is the SG updates. So basically, because we want to derive the function, we want to have a equation to capture the the entire loss dynamics. Instead of like in the optimization theory, the classical stochastic optimization, you only need to derive certain upper bounds. That will be easy. Here we need a accurate capture of the dynamics. So it's actually easier to use in continuous time analysis. But we cannot directly, one important observation is that you cannot to take the continuous time, so that means you cannot treat the time, the continuous time, as a number of steps. So it's more important to consider we call intrinsic time. So basically, because the learning rate is actually decaying. So if one data because if the optimizer goes through one data with learning rate like 0.1, another data goes through the data with steps with like learning rate 0.01. So even there are same total number of training steps, but the optimization actually happens in different program, different rate, because the training time, the intrinsic training time is the sum of the learning rate. So if we use this, if you take continuous limit in this intrinsic time perspective, then you got the continuous time limit given by these equations. We call the intrinsic time stochastic differential equations. So basically, the first part is the gradient flow. Okay, it's the gradient of your target functions, the loss functions, and this one, this is the batch size, and this is the noise covariance and the eta t. Here I need to clarify that here the eta t is the learning rate at the intrinsic time t. It's not about for example, it's not the learning rate at the step t. It's the learning rate at the intrinsic time t. For example, the learning rate at this time is actually eta k. So this eta t is the continuous formulation of this one. Okay, with this with this continuous time limit, we can, so then for this toy problem we present, we have the following functional scaling law, or intrinsic time function scaling law. So this scaling law is, for example, under some assumptions, okay, not important assumptions. So at the intrinsic time t, the loss can be decomposed into irreducible loss, approximation error, called signal learning, and noise accumulation. So there's 4 terms. And here it's not a upper bound. It's actually for each f star. It's a pointwise. It's not a upper bound like the classical optimization theory. We have an upper bound for and also a minimax lower bound. Here it's not a upper bound. It's actually for each f star. For each machine learning problem f star. For each f star, we have at the intrinsic time t, we have this very clean expressions. And this functional scaling law captures the entire risk curve because the t can be any arbitrarily positive value. So basically t is arbitrary. So that means this actually captures the entire loss curve. And also it's for general linear schedule. For example, the eta tau, you can choose your eta tau. And okay, so as I mentioned that this is we call the functional scaling law. It's pointwise for each f star, not just the worst case bound. So let's look at each term of this functional scaling law. So the model size, this one is a model size scaling. It depends on the intrinsic difficulty. Oh, so I forgot to mention that. So basically, you can look at the f star. So it's actually the difficulty of the f star is the intrinsic difficulty depends on the s times beta. But S is actually the relative difficulty because for the same f star, if you're choosing different beta, you have a different S. For example, if you choose a high capacity model with a small beta, you will have a larger S. That means the task become easier. So this is very intuitive. Like the difficulty of a problem is not so that's a relative difficulty. For example, some problem is easier from the smart student. The same problem, okay, the same problem. It may be easier for the smart student, but it can be very difficult for the ordinary the other student. So we use the S to denote the relative difficulty. So now you can see that the approximation error actually depends on intrinsic difficulty, okay? But the signal learning, so this signal learning comes from the gradient descent. So this blue part comes from this gradient flow term. Because the gradient flow, when we do gradient descent, we're actually to learn the information, learn the signal from the data. So we call this term signal learning. And this term is intrinsic-time scaling. It depends on relative difficulty S. So that's very interesting. So that means if you are solving the same problem using the same algorithm, gradient flow, gradient descent, but with different models, the convergence rate is different. If you are using a high capacity model, the problem is becoming easier. S is larger, and the gradient flow converges faster. So that in this part, to explain why it happens in practice, it's a very common observation. Solve the same problems using the same optimization algorithms, but the different models can converge very different. Typically, large model converges faster, and the small model converges slower. And then the last term is called we call the noise accumulation because it captures how the gradient noise accumulated during the training. And this term is actually it's a convolution functional because the eta is the learning rate function. So it holds for any under some mild regularity conditions for the learning rate schedules. So it's a functional term. And we call the K beta is a forgetting kernel because it quantifies how fast the previous introduced noise is forgotten. So for example, it depends on let me show. So eta tau is actually the size of the gradient noise at the time tau. And in the time tau, you do one step gradient descent. You introduce the gradient noise into the system. And this noise, the size of this noise is proportional to the learning rate, eta tau. And during the training at the time t, this noise is a dissipation. It's gradually forgotten, and the K beta capture the forgetting mechanism. So basically, you can see that one of the interesting observations that for high capacity model, the small beta, it actually forgot noise slower. So basically, the small model, high capacity model tends to forget noise slower, and the low capacity model tends to forget noise fast. It's a very intuitive. So okay, I already explained each term of the functional scaling. So basically, there's some trade-off. So you can see there's some fundamental trade-off. For example, the blue one and the red part. So basically, so you can ask the questions: what's the good learning rate schedules? For the blue part, this is the gradient flow or the signal learning. For the signal learning, we want to the intrinsic time, the optimization intrinsic time to as large as possible, right? So the consequence you should choose a very large learning rate as large as possible. Keep a large learning rate as possible, right? But on the other hand, if you choose a large learning rate, then it will introduce a large noise. So basically, there's a trade-off the noise forgetting. noise accumulation and the signal learning. And okay, so it's intuitive, but the difference is, okay, the difference in the functional scaling, we actually have an analytical quantification of this trade-off because we have the explicitly expression for this term, the two terms. Another insight, I want to explain how the power law emerge. So basically why this is, so basically you can look at, so the approximation error is power law about the number of samples, a number of parameters. And the signal learning is power law about the intrinsic time. And the noise forgetting, the forgetting kernel is also follow power law about the intrinsic time t. So where this power law comes from? So this can be explained from a multi-skill perspective or multitask learning perspective. So if you look at so let's just focus on the most simple case. Let's consider the full batch gradient descent without the noise, gradient noise. Let's delta J represent the error to learn the J's skills. Okay, this is the error of the learns the J's skills. Because we still only have M parameters, we can, and also this is actually linear regression, essentially a linear regression, right? So for the top M features or top M skills, the learning follows a linear recursions. It's a linear ODE, linear audio differential equations, and for the remaining skills, it's done. Okay, we do not. It's impossible to learn from data. So basically the gradient, the dot, okay, the derivative of delta J is 0. And if you look at the gradient, the error of the population error minus the irreducible loss, we have this one. So why we have this one? So first, for each coordinate or each skills, each subtask, because it's a linear dynamics, linear ODEs, so the solution must be exponential. It's not straight, right? It's because it's a linear ODE. But when we talk about the training error, the error is actually the average of many coordinates or many subtasks. And then because we already assumed that the lambda J and the theta J star follow certain power law. So even functions for each coordinate, the scaling about the time t is not a power. Okay, it's not a power, but the average, if you average out many coordinates, then the average, the collective behavior of this average will give us a power law. So basically the power law comes from the average. So it happens. So basically that means in practice we can observe power law is because our objective function or our learning problem is actually can be viewed as certain multitask learning, and the number of tasks can be infinite many. That's infinite many tasks. And it also happens for the model size scaling. So so basically I want to emphasize that the emergence power law for this very simple interpretation, the emergence power law actually comes from the accumulation effect. I'll use the statistical physics language is like it's a collective behavior, because then it requires the number of skills and the number of tasks to be infinite many, or to at least sufficient to be large, or ideally to be infinite. And then we can present certain, okay, this is a figure to, because our function scaler is actually derived from the continuous times SD modeling. And this figure is show you that function scaler can also accurately capture the aerodynamics for the discrete time SGD. So basically the solid, so this the fluctuated curves, corresponding to the discrete time SGD, and the smooth curve corresponding to functional scalar prediction. So you can basically see for the different schedules, the functional scalar capture very well of the discrete time SGD. Okay, so with the Okay, so when we have function scale, then a natural question is, in the function scale, the linear schedule can be general, right? Can be arbitrary. Then the natural question is, can we derive certain very explicit schedule for the final step risk by using certain popular linear schedules? That means we can recover classical functions, classical schedules to study how the linear schedules will affect the scaling efficiency. So here we consider three linear schedules. One is the constant, and the second one is exponential decay, and the third one is a WSD-like. It's a constant follow exponential decay. And also in this case, we will decompose. So basically, the problem actually falls into two regimes. One is the easier regimes, when the relative smoothness of the target function is large. Then this quantity, we call this is the easy regime. And also if smaller than this one, it's called the hard regime. So by using our function scaling, you can derive for the scaling, the final step loss scaling for the different linear schedules, for constant exponential decay and the WSD. You can see that. So basically, you can see that compare the different linear schedule. We'll see the WSD is the best. It's a better than pure decay, exponential decay, and the exponential decay is better than the constant. So, for example, you can look at the constant schedule. It only depends on so it have the same rate for the different regimes, and more importantly, it only depends on relative difficulty of the problem. But for the exponential decay, it actually depends on the intrinsic difficulty of the problem. This is what we want. If you, of course, if you compare this rate, and the exponential is actually better than the constant, the rate of the constant. And this is experiments validation. So because this one is still derived from the continuous time formulation, the stochastic differential equations. And if you do some experiment for the discrete time SGD, you will see the derived rate holds very well for the SGD. Okay, so this means the linear schedule actually, okay, it will impact the scaling efficiency. Then the next natural question is, or the final question is, what's the optimal linear schedules? Okay, what's the optimal linear schedules? This is doable in our case because we have the functional scaling. It can capture the functional map from the linear schedule to the final step loss. Have this functional. Now we only need to do some variational principle, do some variational calculation. So okay, so basically, okay, we will before we do the variational calculation, we need to introduce another linear rate. We call this is a this linear rate function in terms of training steps. This is because we need before we do some training, the variational analysis, the constraint, our constraint is the total number of steps given total steps, n steps. So we need, So basically, we want to minimize this, the objective of the function scale. This is a signal learning, and this one is the noise accumulation. Because we already apply a change of variables compared to the function scale I presented earlier. Because here we need to reparameterize using the number of steps instead of intrinsic time, because our constraint is imposed on the total number of steps instead of the total intrinsic time. So basically, the T is the total intrinsic time. So phi z is the linear rate at the step z, because we have the total steps n. So this is the intrinsic time equality. And we also have some constraint about the linear rate, the size of the linear rate. The linear rate must be positive, and it also must be bounded from above, because there's a stability condition. The linear rate cannot be arbitrarily large, because if the learning rate is large enough, it will break the stability condition. Your system will just blow up. Then you only need to derive the, write down the Euler-Lagrange equations and you do some analysis. We have the following optimal learning schedules. First, it also depends on regime. First, for the easy regime, the optimal learning schedule in terms of training steps is given by this one. So basically, it's a power law decay. It's a power decay. So it is a 1 minus z to the certain power. And the optimal learning rate also needed to, so the peak learning rate, the maximum learning rate. And then, so at the steps 0, it follows a maximum learning rate, have a max learning, then decay the learning rate with this power law, power decay. And then for the optimal learning schedule, so the peak learning rate is not a constant. Because you should scale your peak learning rate with the total training data, the data budget. If you optimally tune your learning rate, peak learning rate, and the decay shape is given by these expressions, then you have the optimal error risk. Okay, it does not matter for this one. The interesting things happens for the hard regime. So in the hard regime, if you look at these factors, so it's S minus this one. So if 1S is bigger than this quantity, then this is so this factor is a negative. So there's no problems. But for the hard regime, if S is smaller than 1 minus 1 over beta, then this becomes positive. That means your learning rate needs to scale, grow with the total training steps. This is impossible because your learning rate must be bounded above by a constant. It cannot grow up to infinite, right? So that means that's the reason why in the hard regime actually the optimal learning schedule is different. So basically, you can prove that in this regime the optimal schedule is given by these expressions. For the first N1 step, you should choose the learning rate as large as possible, and then you decay the learning rate following the following the same power decay as the easy regimes. And also the decay ratio of the optimal decay ratio of the decay phase is given by this one. And by some calculations that tell us the alpha is bigger than 0, is positive. That means the decay ratio for the optimal learning schedule, the decay ratio, the ratio of the decay phase only occupy little 0.1 proportion of the total training steps. So this is consistent with the practical usage. As I mentioned earlier, in practice, when we're using the WSD, we always keep a constant learning rate for a very, very long time, only decay the learning rate near the end of the training. So this is, basically this provides theoretical explanation or guarantee why only decay the learning rate near the end of the training is good enough. So, but here this explanation is not. It's just a theorem. Okay, it provides theoretical guarantee. But we actually have a very intuitive explanation why in the hard regime, the optimal learning schedule must be a WSD-like shape. So, for example, if denote the Tn given the total number of training steps n, and denoted by Tn the intrinsic time, then we know the optimization error decomposes two terms: the signal learning and the noise accumulation. So for the hard problem, that means S is small. So if you look at the two terms, they're very important observation. That is, for the GD term, the relative difficulty of your tasks. However, the noise accumulation, it only depends on beta. It does not depend on S. So the noise accumulation quantify how noise accumulate during our training. So it does not depend on the signal, the target functions. It only depends on the size of the noise and the model. Okay, high capacity model tends to forget the noise slower. So that means when S is very small, this term must decrease very, very slowly. And the rate of this, so if you pick up a learn rate, decay learn rate, this term decay with a rate, that rate is independent of S, is independent of the difficulty of your task. The noise decay, the noise dissipation is independent of your task difficulty. So that means for the very difficult problems, when S is very, very small, this gradient descent must dominate the noise accumulation. So that means for this hard problem, the optimization is difficult. It's not because we cannot reduce the noise. It's actually because the gradient descent converges too slow. So then, okay, then if you want the gradient descent to decrease sufficiently, then the only choice is keep a constant learn rate, keep a large constant learn rate as much as possible. And because the noise term can decay with a rate, a sufficiently large rate, so you only need a very small portion of your training to decay the learn rate, then reduce this one. So if you look at the two-phase dynamics, okay, so that means in the stable phase actually do some fit the signal aggressively. But for in the loss curve, you observe the loss saturate. It's because the noise accumulation of the noise, because this term actually becomes gradually dominate. Okay, it becomes larger than this one. But actually, but it does not mean the training it does not happen. Okay, it's actually the model is actually still fit the signal aggressively, but it's dominated, so it's occupied by this one. You cannot observe the signal learning by just looking at this loss curve. And in the decay phase, so basically the decay phase is just drop this noise accumulations. So that means when you in the practical training, if you're using WSD, if you observe the loss dynamics saturate, you shouldn't decay the learn rate. You should still keep the constant learn rate, and as much as possible, and using a very small portion of steps to decay learn rate. Okay. So follow our previous understanding, we can also explain some the popularity of the cosine schedules. If we look at the cosine learn rate schedule, the cosine schedule have two, for example, globally, the cosine schedule, if you calculate intrinsic time of the cosine schedule, the cosine schedule is actually half the number of steps, because it decay very slow. So the total number of steps, total number of training time is proportional to the number of steps. And also if locally, if you do some tile expansion for the cosine schedule near the end of the training, the final steps, we will see that near the end of the training, the cosine schedule actually decay to zero with decay to the minimum learning rate with a power decay. Okay, and this understanding can also explain why the polynomial schedule, the classical polynomial schedule is a bad idea. Because when the problem is hard, we also, as I mentioned, that for the hard problem, when S is small, intrinsic time is much important than decay, than the reduce the noise. So, for example, if we use this polynomial decay learning rate, if alpha is 0 and 1, it will, okay, you can see that the total training intrinsic time, the scale sublinear with the steps, total number of steps. So in one word, the polynomial decay learning rate cannot provide sufficient intrinsic training time. So this is a big problem for the hard problem. For the hard, when the difficulty, the task difficulty is large. So it's not a problem for easy. If you are solving an easy problem, it's not a problem. It's not a big issue. But you are solving a hard problem, it's a big issue. And finally, we also did some experiments for the large language model pre-training. And in these figures, for example, we trained 400 million llama models and 1 billion llama models using the 20 billion tokens. And we assume that the large language model loss curve also follows the functional scaling law, but with the parameter like S and beta is unknown. We fit the S and beta using the data. For example, we're using the blue curve to fit a functional scaling law. Then we can show that you can show that the fitting is actually quite well, and then you can make a prediction for the green one, for the WSD schedules. You can see that the function scaling can even it can also fit and predict the large language model pre-training loss curves. And this part that if you already fit the function scaling law, then a natural question is, as we did the variation calculations, we can also minimize the final step loss using the fitted function scaling law, right? So basically, in these figures, so to see what's the optimal linear schedule in practice, okay, not only theoretical, what I mean in practical LLM pre-training. So basically, the red one is the optimal schedule by minimize this fitted function scaling law. You can see it's still the WSD. It's WSD like, but the difference is it seems that the decay phase is slightly larger than the one used in practice. Okay, and moreover, if you run the experiments by using this optimized linear schedules, you'll see that it actually also improves the final step loss. So basically the red one is a performance better. If you look at the final step loss, it's better than the other one. Okay. So in the summary, so basically in this talk we present some theoretical insights. So I want to convey that the power law kernel regression or some linear regression can be some toy model to reveal certain essential aspects of large language model pre-trainings. So basically, I mean the large language model it's a very complex problems, but some aspects of the problem can be reviewed by using certain toy models. And also the function scaling we derive provides a principled approach to study the loss dynamics. And some practical insights, that is the emergence power law scanning actually from the multitask. So it's a collective behavior, okay? So it's a accumulation effect. And we want to say that intrinsic time, instead of the number of steps, plays a more critical role in characterizing the influence of linear schedules. And lastly, we already mentioned that the optimal schedule, if I are solving hard problems, then the optimal schedule is WSD. It's not a pure decay schedule. It should be keep a constant for as much as possible, and only decay the learning rate near the end of the training. This is okay. Thank you.
Thank you very much. Now we have some time for questions.
Yes, can I ask a question?
Yes, please.
Yeah.
Okay, Professor, thank you very much for your talk. So my first question is, can you go back to the setting of the power law kernel regression? Can you please explain again the basic, the one
here?
where you, yes. Can you please repeat the setting here once again?
So basically, we assume that the target function is a summation of some basis function, right? Actually, I don't know what's unclear here. So basically, you can assume is a summation, a superposition of some basis functions, and the phi j is the basis functions, and we assume that the basis function is covariance of them is Gaussian, and the covariance is diagonalized. But this assumption is just for simplicity. It can be relaxed. It's not necessary to be Gaussian, and also it's not necessary to be diagonalized. Okay, just for simplicity here.
So my question is, why are phi random? Where is the randomness coming from?
So for the target function is deterministic. It's our model. So basically, if you have a student model, because the model uses a projection of the full features. So the feature so basically, if we interpret the phi as the feature map, right? The feature map input the data, map the data to a feature space, a high dimensional feature space. But your student can only use the projection of your full feature in a certain one m dimension. For each one the wj is a random. But wi is random. Wi is random. It's a Gaussian.
Okay, thank you. I understand. And my second question is, so you basically showed that we cannot observe signal learning just by looking at training loss, because the training loss looks like it's saturating. Actually, there's still some learning
because
going
the
on.
training loss is combined actually 4 terms.
Yes. So my question is, do you know of any ways of what other methods there are to observe signal learning in practice? What other quantities we can compute to check if we're actually learning anything?
Yeah, I think you asked very great questions. Very, very good questions. I don't know any other way. So basically, when in practice, we can only, record the loss value in each steps. But this loss is actually can be decomposed to 4 terms. It would be very helpful if we can, observe this one, right? So actually, our practical function scale, our function provide a way to do this, to do it in practice, not only theoretical. For example, if you have a loss curve, you can fit this ansatz. You can assume S and beta is unknown. The sigma S and beta is unknown. You can fit these equations using the loss curves, and as long as the fit is well, have the signal learning terms. I think this is a way. Actually, we did some experiments recently. I don't know other way to, decoding the signal learning component from the loss curve. I don't know.
Oh, okay. So it looks like a very interesting problem, I think. And
Yeah,
do I
agree.
yeah. So do I understand correctly that maybe when training a large language model, you can do the first half of the training, and then from that try to figure out S and beta, and then using S and beta try to try to do the second half of the training more optimally. Would that be possible?
I think so. Actually, this is this ongoing project. I'm doing, but there's some until now. I think there's some problem. In principle, it's doable, but in practice, there's some difficulty. No,
Like,
I think it's.
what
No.
comments to
You are right. You are right. At least the idea you mentioned is doable. It's completely doable. It's doable. Yes. You can train for short durations and fit function scaling law. Then you optimize the function scaling for longer, much more number of parameters of steps. You got a linear schedule, and then you use that schedule to train your model for longer steps, longer duration, right?
Yes, that's what I'm asking about.
Yeah. Actually, we are trying it, but I haven't tried this idea. I try some other idea. A good idea. I should try it. Yeah.
Well, thank you.
Okay, thank you.
Other more questions?
Yes, so maybe a naive question regarding the experiments. So, if you believe that with these different learning rate schedulers, you find very different optimas in terms of like, is it true that the model converges to really different optimas, and are they different somehow in a sense that maybe different rates of step size decay, maybe they give different stability of this optimum. For example, one is more robust than another. Is it possible to measure it somehow? Or
Okay, so first, I'm not sure I fully understand your questions.
because
I think
before
in this
remember,
case, we only care about, for example, for the power kernel regressions. There's only one minimizers. There's no.
yes, of course.
So basically, in the LLM pre-training, we are actually on the under parameter regimes, not over parameterized regimes. For large language model pre-training, we are only at, because as I mentioned that the large language model pre-training, we only go through the data for one pass. So in each step, we are using fresh new data. So there's no optimization, there's no generalization issues. The only issue is optimization error. And also the problem, the model is under-parameterized. But if you look at so the large scale experiment I did, we did, for example, this one. The model has 1 billion parameters, but we have 20 billion tokens. So as far as I know, it seems that it's probably not true. It seems that optimization is more about the optimization instead of the different minimizers and or the robustness, whatever robustness or generalization property.
I see. Thank you.
Okay, this is okay. I think you mentioned a very big, very important problem. The large language model for training is actually very different from the the ImageNet, ResNet. The ResNet is a finite sample optimization. You basically go through data for many epochs. So that's some generalization issues and different minimizers problems. But in the large language model training, we come back to the traditional under parameterized regime.
Okay, thank you. Are there more questions? If it is not the case, then thank you very much again for your talk.
Okay, thank you for the invitation.